While we're on the topic of canonical forms, it's interesting to go ahead and present one more canonical form. You won't see this in anything that we exactly evaluate. You won't see it in homework or in quizzes. So that's what that little brain symbol means. It just means for your extra benefit. So this canonical form is the reason why it's called modal canonical form is because it highlights the modes that represent the dynamical behavior. We've talked about modes a couple of different ways already. And so one way we can see that is if you do the partial fraction expansion of your transfer function, then you get each term, and each of these terms represents a different mode. So these could be either real poles, they could be pairs of complex poles, but each of these represents a pole of your transfer function g, and then the corresponding modal canonical form looks like this, where your A matrix is actually just a diagonal matrix of these poles. Your B matrix is a vector of all ones, and your C matrix is the collection of the coefficients of this partial fraction expansion. So it's also interesting to talk about how you get to modal canonical form. So if you start with just another generic state space system where A and B are your input and state matrices, it turns out that your transformation matrix that's going to get you there is to take the inverse of the matrix whose columns are the eigenvalues of the state matrix A. So each column is a different eigenvalue because so if you have all n of your eigenvectors, then that's a square matrix. So if V inverse is your transformation matrix, we can either do this from scratch like this, or you already know that T inverse is your new A matrix, so that corresponds to this. TB is your new input matrix, and CT inverse is your new observation matrix. So this is the new system in modal canonical form. Notice that what we've done is we've created a matrix, and it's useful to, before we go through the derivation, to remember that the poles of the poles of the transfer function are the same as the eigenvalues of the matrix A. So how do we get the eigenvalue matrix? That's what this is. This is the diagonal matrix of the eigenvalues of A. So to think through that, we just multiply A times V. So let's just take a look at this product first. So the matrix A times this matrix of eigenvectors, where each column is an eigenvector. This corresponds to, when you do this matrix multiplication, this vector multiplies all of the matrix A to produce the first column of the resulting product. And so when A is multiplied by its eigenvector v1, that just produces the corresponding eigenvalue lambda 1. So this all comes from the fact that AV is equal to lambda v. That's the eigenvalue eigenvector equation. And so this reduces this matrix vector product into just a scalar vector product. That's what this is saying. And so this happens for each column. And so then we get each of the eigenvalues with its corresponding eigenvector. One way to write this out is then to note that we could separate these scalars into a separate diagonal matrix like this. So now we have this diagonal matrix of its eigenvalues, where the first column is just going to multiply out that lambda 1, second column is going to get that lambda 2, and so on. And so that ends up creating the same thing. These two things are the same. And so we're going to call this diagonal matrix of eigenvalues, this eigenvalue matrix, capital lambda. And then to complete the idea, we need to multiply now. We've just created this product, so now we need to multiply by V inverse. So if we multiply V inverse by this capital lambda times V, then the beauty of this diagonal matrix is that it commutes, which means that this can be moved either direction. This can move around. Usually with matrices, AB is not equal to BA, even in the square matrix case. So you have to have special cases where this is true. And so diagonal matrix is one of those special cases, allows us to move that out in front. So now we have this, and now we have V inverse times V. And that allows us to go ahead and cancel that out because it's the inverse. That gives us just the identity matrix, which then ultimately reduces down to just that diagonal matrix. And so that's why this simplifies straight down into this diagonal matrix, capital lambda. So again, the modal canonical form is another way of writing a state space system such that it highlights and identifies all of the various modes or eigenvalues of that state space system.